Section 3.6 is going to talk about rational polynomials. So that's going to mean we're going to combine some of our work with polynomial functions along with the idea that we're going to look at the ratio of two polynomials and see what the graph looks like there. So this would be an example of a rational polynomial. You've got a polynomial in the numerator and a polynomial in the denominator. They're going to have different characteristics than some of our just regular polynomials. So let's take a look at this one right here. And if you're following along on Desmos, then this would be the equation 2x minus 3 over x minus 2. I want us to take a look at this equation and do a couple thought experiments here. So let me write this equation down. Y equals 2x minus 3 over x minus 2. Okay, that's fine. Is this equation going to run into any problems anywhere? Is there going to be a problem with the domain somehow, maybe? I'll help you out here. The answer is yes. But where? Where's this going to have issues with its domain? What value of x?
When the denominator is 0.
Yeah, when the denominator is 0, so that means x equals what?
0. Or
2. Yeah. When x equals 2, this is going to have issues. And so a lot of times, and I don't want to say all the time because that wouldn't be quite accurate, but a lot of times when you have that denominator 0, you're going to have this feature called a vertical asymptote. So that's this dotted line here. Now I actually put that on your graph. If you were to graph this in your graphing calculator, you probably wouldn't see that. It kind of depends on a few things, but that's your line x equal 2. So that's one of the asymptotes of this graph. Now that's your vertical asymptote. Is there another asymptote in this graph? Yes. And where would that be? Yeah, right by my ruler. Okay, we got the equation of that one. Well, the vertical one was x equal 2. What would the horizontal one be? Yeah, y equals 2. Now you can see where this would come from in a little different way. So there's a different way I can write this. In fact, let's do it by synthetic division. Let's divide this out. Just practice our synthetic division. Since you're divided by x minus something or x plus something, we can do that synthetically. That'd be a 2. This could be a really short synthetic division, right? What number should I put underneath here? 2 and negative 3. Boy, I hope the synthetic division process is pretty easy for you. Now, 0 here. 2 and 0 gives me 2. 2 times 2 is 4, and then a 1. Okay, well, what does that all mean? Well, this is your constant term, so that's equal to 2. What's the 1 stand for? What's the 1 given me there? Yeah, the remainder. Thank you. So the remainder is 1 over x minus 2. So these two things are equivalent. But writing it this way makes it a little bit easier to see what's going on here. So eventually, it looks like as values of x are getting bigger and bigger and bigger, this graph is getting closer and closer to this line. And you can see the same thing numerically here. So let's take a look at this function here. Now if I put in a 1, I get a 1. Not a big deal. We're right here. But that's not values of x that are really big. So let's start putting in bigger values, like a 10 or a 100. And start to think about what happens in this term. When you have, I tell you what, let's make it even easier. Let's put in 102. So you get 1 over 102 minus 2, or basically 1 over 100. This term is going to get really, really small as you put in larger and larger values of x. If you put in 1,002, that's getting really, really small. So eventually, as your values of x get really, really big, what's going to happen to this term? It's getting closer and closer to y equals 2. So that's your horizontal asymptote. Y equals 2. We can kind of see it right there. And there's another way we can look at those and see those as well. I'll talk about that as we go on. But let's talk about this notation. I didn't mention this notation when we covered I think it was 3.2 or 3.3. So let's see what's going on now. Basically, this is a precursor to some of your later classes, which are going to tell you, well, as x approaches infinity, as I'm going out the x-axis this way, what's happening to the y value? Where's that y value going? The y value is going to get closer and closer to what? 2. And then on the other side of things, as we go out towards negative infinity, so you're going out the x-axis this way, the y value is still getting closer and closer to 2. So, okay. Let me throw in a different example of this so we can just practice with this notation real quick. So, bonus example. Let's do the function y equals e to the negative x plus 3. And I want to look at two things. As x goes to infinity, where does y go? As x goes to negative infinity, where does y go? So it's going to help us to look at the graph of this function. You might remember the graph of an exponential. It's an increasing graph, and then we're shifting up by 3. But this negative is going to flip this around the y-axis. So let me just plot that for us real quick. Give myself a new decimals graph to do that. Y equals e raised to the negative x plus 3. Okay. So take a look at the y coordinates as I move out the x-axis. That's the first part of this question here. Where are the y coordinates settling down to? Where does it look like it's settling down to?
3.
Yeah, it looks like it's settling down to 3. You can't get very far before it rounds to the number 3. So, all right, settling down to y equals 3. Good there. How about if we go out towards negative infinity? So we go out the x-axis towards negative infinity, going out this way. Where's the y value going now? As you go further and further out the x-axis. Yeah, it's going to infinity. So the second part of this would be y is going to infinity as x approaches negative infinity. Yay. So just a little bit of notation there for you. And like I said, it's a precursor to classes you'll see later on, not necessarily in this course, but in other courses. All right. Sure. No worries, no worries. So our goal in this section is kind of several goals. First one, we're going to want to find the asymptotes. Second one, we're going to want to find, what the graph of these things looks like. So let's move on to example B here. Now we saw in example A that when the denominator is 0, we got a vertical asymptote. And that's generally going to happen. Not always going to happen, but generally going to happen. So let's see if we can't predict where this is going to have vertical asymptotes. Vertical asymptotes. Well, for that, I want to know where x plus 1 times 4x minus 12 equals 0. Now, one of these you can kind of just read off, just right off of the equation. What's one of the solutions here? Where does this equal 0? What value of x? Yeah, x equals -1, so that's going to be your vertical asymptote. But then there's another one here where 4x minus 12 equals 0. Move the 12 to the other side. Divide by 4. What's that leave us with?
3.
Yeah, 3. So we got two vertical asymptotes. We've got one at x equals 12, or excuse me, x equals 3, and one at x equals -1. All right, so there's their vertical asymptotes. What else can we determine? We can determine the x-intercepts. How do you find the x-intercepts? That's a good question. The x-intercepts are when y equals 0. In our case, our y is being, r of x is taking the place of y. But if we set y equal to 0 or r of x equal to 0, then this is going to equal 0 where the numerator equals 0. We're not worried about the denominator equaling 0. So where does the numerator equal 0?
0.
Yeah, numerator equals 0. So we get 0 equals x squared times, or x squared plus x. Let me factor out the x. X plus 1. And now I see that I got, I can see where I could get x-intercepts. Where would those x-intercepts be? 0 would be one of them. Where would the other one? Say again?
-1.
-1. Now that -1, I overlooked that when I was looking at this problem. That could be a little bit of a problem, but we'll take a look at that in just a second. Our horizontal asymptotes. Horizontal asymptotes. Well, we've got 3 cases for horizontal asymptotes. So let's look at those 3 cases. If the degree of the numerator is less than the degree of the denominator, then I'm going to get y equals 0 is a horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then my horizontal asymptote is going to be just some number, a over b, where a is the coefficients of the numerator, the leading coefficient in the numerator, b is the leading coefficient in the denominator. And finally, one last situation we can have, if the degree of the numerator is 1 more than the degree of the denominator, then we've got to divide things out, and the quotient of our division, not the remainder, the quotient is going to be what's called an oblique asymptote, or sometimes called a slant asymptote. So, aka slant asymptote. So, 3 different possibilities there for us on that one. Let's continue. So we could get x-intercepts at 0 and -1, but notice we got a factor of x plus 1 in the numerator and in the denominator. That's going to be a little bit of a problem. So, okay, let's keep going though. Y-intercepts. How do you find the y-intercept of a graph? Let me help out here. You're going to set x equal to 0. Okay. If I set x equal to 0, what do I get for y? 0 squared plus 0 divided by whatever. 0 squared plus 0 divided by -12 if you wanted. What am I going to get when I do that ratio? 0. So 0, 0. The graph should pass through 0, 0. Nice.
Can you explain that again? I'm sorry.
Sure. You're just putting in x equals 0 to find the y-intercept. Keep in mind that along this line, the value of x is 0. So when I put in a 0 for x, I'll find where the graph crosses the y-axis. So like in the last one, if I put in a 0 for x, then let's see here. Something doesn't quite look right. If I put in a 0 for x, I'll end up with 3/2. Should be the y-intercept. Here, when I plug in a 0, I get 0 squared plus 0 divided by 1 times negative 12. 0 over negative 12, that's my y-intercept.
Oh,
Okay, let's actually look at the graph. It doesn't hurt to graph these things. I've got them graphed on Desmos. You can graph them on a graphing calculator. And the graph kind of disappoints a little bit. Doesn't quite meet our expectations. I thought there was going to be a vertical asymptote at -1 and 3, but there's not a vertical asymptote at -1. We're just getting one vertical asymptote at 3. And the problem is we've got a similar term in the numerator and denominator. So that's what's messing us up here. So let's take a look at that term. R of x can be thought of as x times x plus 1 over x plus 1 times 4x minus 12. In your heart of hearts, what do you want to do with this ratio, with this fraction? What's screaming out to do? Cancel. And you can cancel it. You just got to remember that with the original function, x can't equal -1. There's going to be a problem there. X can't equal -1 because you'd end up with 0 over 0. 0 over 0 is undefined, so we'll have to throw that one out. X can't equal +3. That gives you your vertical asymptote, but here you've got a hole in the graph, and it's kind of tough to see those holes. So let's take a look at the graph here, see if we can't spot that hole or figure it out. So I'm going to slowly trace along this graph, see if I can't get that hole to show up. Yep, there it is, right there at -1. Yeah. It's in there. I think you can see it flashing by. There we go. Don't breathe. All right. So there's your hole. You can get that to show up on your graphing calculator as well if you position things in the right spot. So the right spot would be to center your graph at -1. Let's see if we can come up with something that's centered at -1. So we'll plug in the function. Uh-oh, there we go. By the way, you can do the periodic table on your graphing calculator. Just a kind of quick FYI, it's pretty cool. Well, let's put in the function. I'm going to put it in with parentheses. You can use the up and down fraction bar, or just the horizontal fraction bar. X squared plus x divided by, and I need 2 sets of parentheses. One for the entire denominator. So this is x plus 1, and then 4x minus 12. So one set of parentheses closes off each binomial term. The other parenthesis closes off the entire denominator. Now if I want a window that puts -1 at the center, well, let's see. I'll go, we'll do -1 minus 4. That'll give me 1 point. And then I'll do -1 plus 4. And that'll give me another point. Great. So now I've got -1 as a center. And let's graph it from maybe -10 to 10 on the y-axis. Scale of 2. Not quite seeing that one. If you hit the trace key, when you try tracing it, what y value am I getting when x equals -1? Nothing. It's just not defined. Yeah, that's because this, normally you'd be able to see it, but we can't quite see it because this graph is passes right through the x-axis at that point, so we can't quite see it. But generally speaking, if you do set it up like that, it will work. You will be able to see a hole in the graph. Now, let me make it a little bit clearer. I know it's a different function, but if I add, say, 2 to this graph, we should be able to see the hole. There you go. That's typically what you'll see. It just happened that our hole was occurring at the x-axis. All right. So what do we got here? Does the graph have a hole? Yes. At x equal 1, the graph has a hole. Our x-intercepts, well, there was one of them that was at 0. At x equal 1, we had a hole. Actually, this should be negative 1. Okay, let's move on to example C here. Did everyone get a handout? Seems like you got a few extra here. Okay. So there's really no calculation here. I just kind of want to test you on a few things here. Is there a vertical asymptote for this graph? No, there's not. It has a dip, but there's no vertical asymptote. So, no. No, none there. How about x-intercepts? Are there any x-intercepts? Yeah, where would the x-intercepts be? Yeah, thank you. 4, 0, and negative 4, 0. Remember, you would find those by setting y equal to 0 and solving for the numerator is equal to 0. What else? Horizontal asymptotes. Got one of those? Yeah. What's the horizontal asymptote?
2.
Yeah. Y equals 2. Please be careful on an exam. If you give me just 2, I'll be unhappy. Do you mean x equal 2? Do you mean y equals 2? Is that part of a coordinate? It's just a little too ambiguous. So I typically will give me the equation of an asymptote, and I'll put that in italics and bold, etc., because I want an equation. Don't just give me a number, please. Does it have a y-intercept? What's our y-intercept here? Yeah, negative 6. So 0, negative 6. And again, you would find that by setting x equal to 0. X equals 0 will tell you where this graph crosses the y-axis. Nice, nice. Okay, let's flip it over to the next page here. Now, those of you who are here right at 10, give you a chance to write this down ahead of time. But it's really that little sheet that I passed around. This one right here, kind of saying the same thing. We're asked to find some horizontal and vertical asymptotes for this graph. So let's start with the vertical asymptotes. So this is example D. Example D. So our equation is what? 16x squared plus 1 over 4x squared plus 10x minus 14. First things first, if we want to find the vertical asymptotes, what do I have to do? What should I do to find the vertical asymptotes? Griffin, any suggestions? set the denominator equal to 0. Great. So that's going to be 14x squared plus 10x minus 14 equals 0. Who feels like using the quadratic formula? Yeah, me neither. All right. Liv is giving me the biggest, like, oh man, that's almost as bad as eating lima beans. Yeah. So, all right, for me it would be lima beans, but it might be different for you. In any case, so let's do a little bit of a workaround here. Since we're not really interested in trying to solve this, why don't we just graph that parabola? We'll graph y equals 4x squared plus 10x minus 14, and wow, looks like it crosses the x-axis at 2 places. One of them at negative 3.5 and the other one at 0. So let's write both of those down. So I've got, no, I said 0. One of them at negative 3.5. The other one was what, 1? I think it was a 1. Yep, 1. Now let's see if we can't rewrite this a little bit. Negative 3.5 would also be negative 7 over 2. Okay. So I'm going to see if I can't figure out some binomials for this. Actually, I don't really have to, but I will. Let's take x equals negative 7 halves. I'll multiply both sides by 2. I get 2x equals negative 7. Or moving the 7 to the other side, I get 2x plus 7 equals 0. For my x equal 1 term, that's a little easier. So, all right, I've got the factorization. I can tell where I'm going to have my vertical asymptotes. I'm going to have vertical asymptotes at 1 and at negative 7 halves. But by the way, as a nice little aside here, this also gives us a way to factor this polynomial, right? There's a greatest common factor of a 2. I can factor that out. That leaves behind 2x squared plus 5x minus 7. And then the rest of it can factor with these two terms here. You've got 2x plus 7 and x minus 1. Nice. So, quick workaround in terms of factorization. Not that this completely replaces the quadratic formula, because sometimes you're going to have complex solutions and irrational roots, so you're not always going to be able to do this, but in this case it works out good. So we've got our vertical asymptotes.
Wait, so what? Which part is
These two. X equal 1, x equal negative 7 halves. Those are your vertical asymptotes. What about the horizontal asymptotes? For the horizontal asymptotes, what you should notice is that the degree of the numerator equals to the degree of the denominator. Both of them have degree 2. If that's the case, then I get a quick horizontal asymptote. Where is this graph going? Well, it's going to be the ratio of the leading coefficient in the numerator. What's that leading coefficient in the numerator? Coefficient of my highest degree term. 16. That's the coefficient in front of the largest degree term of x. So that's your leading coefficient. What's the leading coefficient in the denominator? 4. Can anyone simplify 16 over 4 for me? Yeah. So overall, I'll get y equals 4 as my horizontal asymptote. It's just the ratio of those leading two numbers. For our vertical asymptotes, I'll fill this in. We've got x equal negative 7 halves and x equal 1. I guess I didn't need to put the x equal. They already have it there for me. The domain. What's the domain of this function? Well, for the domain, we can't plug in a -7/2 and we can't plug in a 1. So we got to plug in everything else but those. So let's see if we can't figure out the domain. It might help you to draw it all out. -7/2 and 1. Typically speaking, you're going to be asked for domain and range in interval notation. So, Lena, what will be the interval to the left of -7/2 here, please?
11 for me, and 7.5 parentheses.
Yeah, -infinity to -7/2 with parentheses.
And
Keep going.
comma 1 parentheses.
Mm-hmm.
1.
There's your domain. Basically, we want to avoid these points. Thank you very much. So there's your domain. The range is a little bit harder. So -infinity to -7/2, -7/2 to 1, and 1 to infinity. The range, like I said, is a little harder. You're going to have to look at the graph. Let's do that. Let's put in the asymptotes. There's your hole in this graph. Oh, see, that's the wrong one. Sorry. We're in example D here. So this is kind of a funky looking graph. Let's put in some asymptotes. We've got vertical asymptotes and a horizontal asymptote, but it feels like there's a little bit of a gap in this function. Let me zoom out a little bit. Yeah, this graph has a gap between here and here. So that gap is not going to be in the range. I'm kind of surprised that they would put that one in here. Okay, so the range would be -infinity to this, and then here to +infinity. It's missing these numbers, these values of y in between here. Let's not get confused with the asymptotes here. Let me shut those off and zoom out a little bit. But the graph has this little bit of a gap. I'd be a little bit nicer to you on an exam. All right, finding these would be a little bit more work than it's worth. So we'll skip that one for this part. And that's it. That finishes off our graphs. Let's practice graphing this on your graphing calculator. If you don't have one, come up and borrow one. If you do, bust it out. But I get kind of frustrated when I see people graphing these things on exams and they're completely off. You should be able to get a decent looking graph from your graphing calculator. Okay, so let's see here. I'll give you a couple different options to put in the function here. So I'm just going to clear out what we have here. Now the one that all of you can do would be this, and that is we're going to put parentheses around the numerator, 16x squared plus 1 divided by, and they need parentheses. If you don't get the parentheses around the whole denominator, it's just not going to work. 4x squared plus 10x minus 14, and then a right parenthesis. So that's one way. If you have a fancy up-to-date TI-84, another thing you can do would be to give yourself a horizontal fraction. Most of you on your calculators can do this. You can hit the alpha key, then the X key. That'll give you this green key right here. And now I don't need to worry about parentheses because I've got a nice horizontal fraction. It's 16x squared plus 1 divided by 4x squared plus 10x minus 14. So either way works. It's just whatever you find convenient. I do like the horizontal fractions because people make less mistakes with inputting the function and then their graphs. Now, as far as the graph is concerned, you might look at that and go, I have no clue where to even begin graphing this. If you don't have a clue where to begin graphing this, then there's a nice kind of default that's built into your calculator. Do you remember where it's at?
Zoom 6.
Zoom 6, yeah, well done. Zoom 6 gives you the standard window. It's not a bad place to start. It actually looks pretty good here, right? You can kind of see your horizontal asymptote up at around 4. In fact, you could add that in if you wanted to your graph. Just type in a y equals 4 and see that, yeah, it's getting close to that. So the standard window actually works pretty good. All right, looking good on that graph. Yeah, I'm not sure I'd change much if I was going to play around with the window. I guess the only thing I might do would be add a little bit more to the left, maybe negative 15, and then a scale of 2 or 3. But, you know, that's a good looking graph, even with the standard window. Let's keep it going. Let's move on to example E, unless there's some questions on example D here that maybe I went over too fast. Okay. Example E. I don't think I want to do a separate sheet of paper on that one. S of x is 6x minus 18, x minus 6 times x plus 1. Okay, let's find a few things here. Starting with our x-intercept. How do I find my x-intercept? Nicholas, how do I find my x-intercept? That was cute. You looked just like, does it mean me or does it mean, you know, Nicholas? So right. I just threw it out there. I'm like, all right, one of them will answer. All right. So yeah, we're gonna set x-intercept. We're gonna set y equal to 0 or set the numerator equal to 0. All right. Awesome. So it's gonna be 6x minus 18 equals 0, or x equals 3. No, it's the numerator equals 0. Yes. So it's the numerator equals 0. Let me show you why. Let me get a different sheet of paper and show you why you're setting the numerator equal to 0. So if I have some polynomial, call it r of x equals the numerator polynomial over the denominator polynomial. If I want to know where x equals 0, or excuse me, yeah, if I want to know where the y coordinate equals 0, that's putting a 0 here or a 0 here, so I get this. So I end up with, oh, I'm sorry, I didn't realize I was off screen. I wish you would have said something. Here's my rational polynomial. You can write it as y, you can write it as r of x, but it's p of x over q of x. Some polynomial in the numerator divided by some polynomial in the denominator. If I want to know where the graph crosses the x-axis, that means where y equals 0. So I'll put in a 0 there. Okay. But now I'm looking at this and going, you know what? I've got a fraction. I don't really like fractions. So what I've told you throughout your math career, at least as long as you've been with me, is if you got a fraction in an equation, get rid of it. You can multiply both sides by the lowest common denominator. In this case, it's q of x. what happens when I multiply the right-hand side by q of x? Do you see any simplification? These maybe cancel. Can anyone help me out on the left-hand side? What do we get on the left-hand side when I want to multiply by q of x? 0. Something times 0 is still going to be 0. So all I'm left with is p of x equals 0, which is exactly the numerator. So when the numerator equals 0, the graph crosses the x-axis. You don't have to worry about the denominator part for that. So that's a good thing. It makes our life a little bit easier. And in this case, it's at x equals 3. So if you're keeping track of some points, x and y, if I put in a y equals 0, I get x equals 3. Okay. What do I do to find the y-intercept? So where the graph crosses the y-axis, what value does x have? Yeah. So we're going to set x equal to 0. So s of 0 is going to be 6 times 0 minus 8. Excuse me. 18 over 0 minus 6 times 0 plus 1. Lots of zeros here. 0, 0, 0, 0. You're going to end up with negative 18 over negative 6, which is also a 3. So we're getting kind of this weird symmetry of points. 0 for x gives you 3 for y. Okay, it's not always going to happen that way. That's all right. Just kind of something a little different for us in this one. Let's take care of a few other things. Yes?
How does that, what about the 1 in the denominator?
Negative 6 times 1 would be negative 6. Yeah, no, I appreciate that. Thank you. Just so you know, you gave my heart a pause. I'm like, oh, don't tell me I made a mistake. I feel so bad when I make mistakes. I just do, you know. And sometimes it kind of depends on the audience, you know, the students. Sometimes people are really cool about it. You know, they'll just gently erase. That's fine. And then other times you get the angry eraser. And then occasionally you get the really loud protest of, and I just feel bad. I try not to make mistakes, but hey, I'm human. All right, let's take a look at the vertical asymptotes then. Vertical asymptotes, I'm hoping you can read those off. What are the vertical asymptotes in this particular case? No? I'm wrong? You can't read these off? Yeah. So we want to know where the denominator equals 0. So it's going to be x equals 6 or x equals negative 1. By the way, that's also kind of a little bit of a hint for our domain. Will, what's the domain going to be, please? All right, go ahead. This is kind of clever. Negative to infinity excluding.
Those two numbers.
Yeah. All right. In WebAssign, you probably end up having to answer it like this: negative infinity to negative 1 to 6, and 6 to infinity, all with parentheses. I always put the union between though. In WebAssign, you might just be putting a comma. Okay, good deal. Let's think about what else we got here. How about the horizontal asymptote? What's going to happen to this in the long run? So the horizontal asymptote. So we've got s of x equals 6x minus 18. Let me multiply out the denominator. Not that you have to, but you're going to get an x squared minus 5x minus 6 if you FOIL it all out. But what's that telling me in terms of the horizontal asymptote? Where is this graph going to go when you start looking at larger and larger values of x? Well, let's take a look at the graph itself. The graph itself. Now, the one thing I want to emphasize is that I'm not taking your graphing calculators away from you when you take the exam. You'll have them. You can do these graphs yourself and kind of confirm or prove yourself wrong for any answers that you have. So take advantage of that. So here's what it looks like on Desmos. Let's also put it in here in your graphing calculator just for comparison's sake. All right. So I'll do it this way. 6x minus 18. And you can leave it factored here in the denominator. That's okay. Your calculator doesn't care. It doesn't have feelings. X plus 1. And I'll do my zoom standard again, zoom 6. So I'm getting pretty much the same thing. But where does it look like this graph is settling down to as you move far out the x-axis in either direction? What's it look like it's getting close to? 0. Yeah, it looks like it's getting close to 0. Is there anything else we have that would make sense of that? This part. Let's take a look at the degree of the numerator. What's the degree of the numerator here? 1. And the degree of the denominator is 2. So since the degree of the numerator is less than the degree of the denominator, eventually this graph is going to go to 0. It's just that simple. And you can kind of understand why. Let's pick a modestly big number like 1,000. If you put in 1,000 in the numerator, I'll get something close to 6,000. But in the denominator, 1,000 squared is 1,000,000. Wow. Okay. So 6,000 over 1,000,000, yeah, the 6,000 is going to get kind of lost in that. And you put in bigger numbers like 1,000,000. The numerator is 6,000,000, but the denominator would be something in the neighborhood of 1,000,000,000,000. And that ratio overall is starting to get pretty small because this numerator is not growing as fast as the denominator, not by any means. Okay. Looking good on that one. Looking good. We got the domain, the range. The range I think we can get off of this one. Let's take a look at the graph. This goes from negative infinity to infinity. And it actually does cross through 0. If it didn't have this little branch here in the middle, then 0 wouldn't be part of our range. But the range here would be all real numbers. So I don't remember our fancy notation for all reals. Yeah, script R, or negative infinity to infinity. Nice.
I have a question. So,
Yeah, please.
the horizontal asymptote in this one, it will be 0?
Yeah, horizontal asymptote is y equals 0. Our vertical asymptotes were at x equals 6 and x equal negative 1. And the domain was negative infinity to negative 1, union negative 1 to 6, union 6 to infinity. Nice. Yes, Don?
So, why is the horizontal asymptote 0?
Because eventually this graph kind of settles down and gets smaller and smaller and closer to 0. So let's take a look at it on our Desmos one. I think it's a little bit wider of a picture. But let me zoom out a little bit like this. As you look at the y values, as you move out the x-axis larger and larger, they're getting smaller and smaller. So when we're out here near 350, take a look at the y value. It's 0.017. And then 0.0012, et cetera. So it's getting smaller and smaller, and it's getting closer and closer to 0. So that's what our horizontal asymptote is.
How would we
You-
recognize that that's something we need to do though, because I look at that and think I'm supposed to be solving something, not that I should
So-
check the points.
So that's one way you could do it. But the biggest thing that I would suggest is this right here. This is going to help you find your horizontal asymptotes. If the degree of the numerator is bigger than the degree of the denominator, then y equals 0 is automatically going to be your horizontal asymptote. So mostly you're going to concern yourself with these first two cases. The first case is that the degree of the numerator is less than the degree of the denominator. That's a nice one. Or in the second case, the degrees are equal, and that's like example D. If the degrees are equal, then eventually your horizontal asymptote is just going to be the ratio of those leading coefficients, 16/4 in the previous example. So it's one of those couple conditions. Now there is a weird condition that we'll see on the back page here. If the degree of the numerator is one more than the degree of the denominator, there's a little bit something funny. That's going to be a oblique or horizontal or oblique asymptote or slant asymptote. Okay. I think this graph almost looks like. No, it's not quite. All right. Why don't you see if you can't test yourself on some things here? So I'll pause yourself. There's no calculation. It's just answering some questions here. Find the x-intercept, the y-intercept, the vertical asymptotes, horizontal asymptotes. Is the function a rational polynomial, a quadratic, a logarithmic, exponential, or radical? And then maybe fill in some notation here. If you're watching this later, pause the video for yourself and give yourself a chance. All right, fill in those for example F here.
For that last one, sorry, I just,
Yeah, go ahead.
sorry, I'm trying to remember what I was gonna ask you. This part right here, is it always going to be, like,
If you're trying to find the x-intercepts, it's always going to be the numerator equals 0. Always.
okay, so you just set the numerator to 0,
Mhm.
then, okay,
Yeah. Which is exactly what we did.
okay.
Okay.
Yeah.
There you go. This graph gets closer and closer to the x-axis this way, and closer and closer to the x-axis this way. Yeah. That's where the graph is getting close to. Can you find the x-intercept?
This is where it crosses the x-axis. Okay, so, and then it's also where it crosses.
Good. How about the y-intercept?
There's a little kind of.
Actually,
result.
kind of-
Sorry. We looked at this and he said that it was, well, he didn't say it was wrong.
Um,
Yeah, because I had my dog and he told me it was wrong.
and that kind of contradicts what you wrote here.
Oh, yeah.
And this is from the trip of her saying, when exit, this one goes down.
So when you go out to the x-axis, so this is getting closer and closer. It seems like it's getting closer and closer to your x-axis. So 0 there.
But that's not,
0 there.
so should I take this one?
So yeah, I'm just, so there's one.
Okay, should I take this one then? I should,
So
then what
maybe-
is it?
Using the vertical axis.
Could be.
Yeah, but it's
vertical.
good here. So I should take this one continuous.
Well, yeah, let's assume that it continues. So, mhm.
I'm pretty.
Okay, perhaps I should have made this clear before I gave things a pause here. But these graphs continue out to the left and out to the right. Let's start out with the first one, which is the x-intercept. Where does this graph cross to the x-axis? 0, 0. And if it crosses at 0, 0, that means it's an x and a y-intercept, so 0, 0 for that one. Now we've got some vertical asymptotes. You have one here, you have one here. So these are a couple of vertical lines. I would hope that you'd be able to come up with these. X equal -2, x equal 5. So -2 and 5. But there's also a little bit else going on in this one. And I'm going to look at it here. As x goes to infinity, where's the y-coordinate going? Where is it getting closer and closer to? What does it look like it's getting closer to? Yeah, 0. And if we go out the x-axis the other direction, as x goes towards -infinity, what's the y value getting close to? Still 0. So in either direction, you're getting closer and closer to y equals 0. That makes it a horizontal asymptote. It doesn't have to match in both directions in order to be a horizontal asymptote, but it does in this case, and that's fine. This is a rational polynomial. That's what's giving it these characteristic vertical asymptotes. You're not going to see that so much for your exponential or logarithmic equations. Well, you will see a vertical asymptote for your log equation. But that's it. There's your graph. Okay. Let's see. Comments on example F. Hopefully kind of a user-friendly example there. Let's finish it up with example G and example H. I think I want to do example H first. Now the part that a lot of you seem to be struggling with is these horizontal asymptotes. So let's decide which of these three cases we're working with, A, B, or C, as we look at example H here. Which case are we working with in terms of an asymptote? What's the degree of the numerator? 2. And the degree of the denominator is 1. Thank you. So does that mean I'm working with case A, B, or C? Okay, case for C. Let me see some votes here. So instead of A, B, or C, hold up a finger for 1, 2, or 3. Which case am I working with? I want to see some hands. All right. Change your vote? Okay. Well, Is the degree of the numerator less than the degree of the denominator? 2 is bigger than 1, right? So it's not that one. They're not equal. So yeah, it is the third one. All right, so, okay. Now, if it is the third one, then what we have to do is we have to divide the numerator by the denominator. Let's do that with synthetic division. Before I do it with synthetic division, let me remind you that there's something missing in the numerator. What's missing in the numerator that I need to account for my synthetic division? Plus a 0. All right, you need to account for the constant term even though it's not there. So for synthetic division, I'm going to have a 1, a 3, and a 0. If I'm dividing by x minus 7, here's good practice for our synthetic division. What number goes out in front? 7. 7 goes out in front. Ethan, what number goes underneath this first number here? 0. Add to go down, multiply to go up. Nolan, run me through this one if you would, please. What should I write here? First step is to add to go down. Thank you. So 1 here, 7 times 1, 7, add to go down, multiply gives me 70. Great. So you get something like this. Hopefully you know your synthetic division real well by this point because you're going to have to use it a lot. But what does that say? It says I can rewrite this. How? What does this mean for me in terms of a polynomial and a remainder?
X plus 10, remainder 70.
Nice, well done. Remember, this is your constant term. That's your coefficient of x, and then x squared, etc. The rest of these are 0. So this turns into x plus 10 plus 70 over x minus 7. But this part of it right here, that's your slant asymptote. Y equals x plus 10 is the slant asymptote. Nice. So that's this thing right here. Y equals x plus 10. Okay, great. So we've got a nice slant asymptote. Like that. Where's our vertical asymptote for this graph? Anyone tell me where that one is? Blake? What do we got for the vertical asymptote?
7.
Yeah, x equals 7. So that's going to be this guy right here. Yep, right there. X equals 7. Nice, so we've got our asymptotes down. Now this is the part that I expressed some confusion on earlier. I'm like, well, I don't understand why people don't just graph these things. And we can. So it doesn't matter which form of these I want to put it in. I could put it in this way, or I could put it in this way. Both of those are the same. In fact, if you wanted to double check yourself, you could put them in both ways and make sure that they overlap. Okay, so let's see here. Y equals, I'm just going to do it this way, x squared plus 3x, x squared plus 3x, divided by x minus 7. And I should get a graph that, starts to look like what I've got. Now I'm going to go back to the standard window. I might need to zoom out from there. So zoom 6. And yeah, I'm not seeing enough of this graph as I might like. So let's take a little hint from the handout. In the handout, I go all the way up to 50 and all the way down to -20 on the x-axis. And on the y-axis, I go from -20 to 40. So let me readjust my window a little bit. So it's going to be -20 up to 50. And then -20 up to 80. I probably don't want to leave x scale and y scale equal to 1. I should probably make that like a 10 or a 20. I'll make it a 10. This one I'll also make a 10. And that looks a little bit better. You're going to really struggle if you want to try and graph x equals something on your graphing calculator, but you can graph the other one. You can graph the horizontal asymptote, or the oblique asymptote or slant asymptote, x plus 10, should fit in our graph pretty nicely. So there you go. Nice. So as far as what I'm looking for on an exam, you'd finish it up with this. Say, all right, it's going to look kind of like this. And the other one I think was tucked in underneath here. Yeah. The other one's going to be like that. All right. Not looking for anything really dramatic. You don't have to plot a lot of points, etc. You could and should be able to find where the graph crosses, say, for instance, the x-axis or the y-axis. All right. And actually, there's 2 points where it's going to cross the x-axis. Okay. How are we looking on example H there? A little chance for extra credit on an exam. It's great if you can find the whole, but it's not something I'm going to worry about in this course too much. But I'll help you out in this one. Let's factor out the denominator. And in the denominator, I've got x times x squared plus 2x plus 7. But it kind of looks like I would want to be able to cancel the x's in both the numerator and denominator, doesn't it? I mean, you can. But keep in mind, even if you cancel it out, the original function itself is not defined when x equals 0. And because you have that factor in the numerator and denominator, x equals 0 is a hole in the graph. It's just not defined there. I mean, it cancels out, but the original function itself is not defined at 0. If you look at the graph and you're really careful, you could probably spot that. Let me see if I can be careful enough here for us. Let's see. Let's zoom out a little bit. Yeah, so right at 0, yep, you see there's a hole in the graph. It says it's undefined. Okay, no big deal. You can also find, let's just do the horizontal asymptote. What case am I working with for the horizontal asymptote? B. So the horizontal asymptote is going to really be the ratio of the degree in the numerator and the degree in the denominator. Millie, what would that be, please? I said the degree, I meant the leading coefficients. But go ahead, what would the equation of the horizontal asymptote be? Yeah. Nice. So it's just going to be the ratio of the leading coefficients. In the numerator, I've got a 3. In the denominator, I've got a 1. Even though that 1 isn't really written, it's kind of understood to be there. So we'll just kind of put a 1 there. And overall, it's going to be y equals 3 is going to be your horizontal asymptote. So that's a very friendly case for horizontal asymptotes. It just settles down to 3. You can see that on your graph as well. Okay, I think that's it here for me for section 3.6. Comments or thoughts on anything, something that you want to look at a little bit more? All right, maybe you want to play around with this one, find the equation of that horizontal slant asymptote, etc. You can do the long division. If you're going to do a long or synthetic division, let me rewrite this for you. Negative x squared plus 4x over 3 times x minus 1. I've factored out the 3. You actually can't use synthetic division the way this stands because the coefficient in the denominator has to be a 1 or a negative 1. Actually, it has to be x plus something or x minus something in the denominator to do that. So you'd have to fuss around a little bit more. You have to use long division there. Okay, that's it for this section. Let me get you busy on some review.